All right, let's get started. Okay, selling 30 freezes every 15 minutes. Unfortunately, they only have enough resources to make 120 freezes today. So there are a couple different ways we could graph it. We could say that the number of freezes is increasing, or we could say that the resources they have are decreasing. And I'm going to use this model just because it's going to give us some helpful examples down here. So we're going to say this is freezes left, and this is minutes. So when we create a table, we're going to say our x is our minutes left. No, our minutes, excuse me. So that means with 0 minutes, they have 120 freezes left to make. After 15, they have 90 left to make because they made 30. After 30 minutes, then they make another 30, and that makes 60. And so on and so forth. So 45, 30, and 60 minutes, they are all out. So if we do the table, this helps us set up how the graph has to be laid up. So we know we have to get from 0 to 120, 20, 40, 60, 80, 100, 120. Okay, good enough. 100, 80, 60, 40, 20. Remember, we have to have an even scale that always starts at 0. And minutes, we have to say this is minutes, so 0. We have to get to 60, so I'll say this is 15 here, 30 here, 45, and 60. That way I'm making enough use of my graph that I can actually see, I can actually write. And then maybe use a straight edge of some kind here. If I can find one, here we go. I'll say we start at 120 and we go, well, we can do each point. So we can say 15 is 90, and then 60, and then 30, and then 0. Now, they're probably not making them in batches of 30 freezes, right? So there's lots of, we would say that there's 30 dots in between here. So that's close enough that we can just draw the line. On this test, I'm not quite so concerned about the solid line or the points, because what we're talking about is the rate of change. There are a couple ways we can see the rate of change, but that's what we're going to need in order to find the equation. So we can look at the rate of change and say, look, from 120 it has to go down, or do it this way so you can see. I have to go 30 minutes, and my number of freezes left drops by 120 minus 60 by 60. So I could do it that way, negative 60, and say, look, this is a rise over run, right? So this is a rise of negative 60 and a run of 30. So you can do it that way. We could also do it numerically, algebraic or arithmetically with the arithmetic, just looking at the change in y and the change in x. As long as we go the same direction and we go between 2 points, we're fine. So this is the change in y, 120 minus 90, and the change in x, 0 minus 15. Notice that I went from this point to this point. If I mix it up, then I'm going to have the wrong sign, and it's going to be, instead of a downward decreasing function, it would indicate an upward increasing function. So we'd get off on the wrong foot there. 120 minus 90 is 30, 0 minus 15 is negative 15. So this simplifies to negative 2. So that's our rate of change, negative 2. Okay? So remember that a whole number is always, we can say it's divisible by 1. And that's helpful because the for every is what the fraction bar kind of symbolizes. So we're saying there are negative 2 freezes left. We could also say 2 fewer freezes, right? There are a couple different ways you could word this. For every 1 minute, right? Because this is our x, change in x, and this is our change in y. So once we have the rate of change, then we can write our equation. Okay? Start with 120, go down by 2 for every x. So here's our y-intercept, and here's our rate of change. Y-intercept is pretty easy to find in this case because it's right there in the function. We'd say that they're going to make 120. Now, again, if you did it a different way and you decide you were to start here, then you'd have going up from 0, 0. So that would be both your x and y-intercept. But in this case, the y-intercept is 120. So in this words mean at 0 minutes, or at the beginning, they have 120 freezes left. That's all it is. Tell me what's happening with x, tell me what's happening with y. In this scenario, since I did it very precisely and I made the table, I can see that the x-intercept is 60. So this means that after 60 minutes, that's where I am on x, they are out of freezes, as in the y is 0. Okay, baseball team, 450 baseballs, begins the season. Ooh, that's a good clue. That's probably where they start, right? And then sure enough, there's our beginning right there in the function. They decrease 50 due to home runs each year. So that's 50 over 1, right? So that's what, both here in the function or in the description and in the function, we have the rate of change. So we say it's going down by 50. Notice that there's a negative there. This means it's decreasing. We need to say that our rate of change is negative. So over 1, that's negative 50. So that means what? They lose 50 baseballs. That's the negative 50 for every 1 year. Okay, now some of you will say, wait, isn't that what the problem says? Yes. Yes, that is what the problem says. We're just looking for you to make sense of it and see that that's actually already in the problem. In this scenario, the y-intercept is 450 because that's where we start. Maybe mathematically you could say, well, the y-intercept is where x equals 0. Right? If we look up here, our y-intercept is where our x is equal to 0. So anywhere you're on that y-axis, that means your x is equal to 0. In this case, if the x is equal to 0, then this is 15 times 0, and that means that it's 0, basically goes away. So that's how it works out in the algebra, in the function. The y-intercept is 450. In words, this means the team starts with 450 baseballs. Now the x-intercept, not quite so obvious, but if we know that x equals 0 for the y-intercept, right? And we know that because that's the start where we have nothing related to x, only the number that we start with. So because x is 0. Our x-intercept is anywhere along this line, right? The x-axis. And if you notice, anywhere you are along this line, you don't know what your x value is going to be anywhere, right? 15, 30, 45, 60. Our x could be anything, but if we're on this line, that means we're not up in here on the y-axis, we're right here at 0 on the y-axis. So we're saying that the x-intercept is where y equals 0. And you remember that that's what f of x also means. They mean the same thing, and just f of x gives us a slightly different way of symbolizing and speaking about functions. So if that's where y equals 0, then I'm saying, okay, where does 450 minus 50x equal 0? What value of x will make this true? So I could add 50 to both sides. Going back to module 1, 50x. So I made a 0 there. Then I've got 50x equals 450. And then divide both sides by 50. And I've got x equals 45, 9. So I'm running out of room here. On the actual quiz, I'll try and make sure I give you enough room. But on the in words, this means that after, this is X, right? So X is representing years, right? So we say after 9 years, Y is 0. And Y represents, or f of X represents the baseballs. So they have no baseballs. Okay, that's the interpretive statement. Okay, here's a function that, you know, chemists and weather forecasters use all the time between Fahrenheit and Celsius. And we notice that this one doesn't start on the y-axis, it starts up here on the x-axis. So, identify the rate of change in the scenario. Okay, rate of change, you'll remember this tool from class, very helpful for us just to write the numbers here in a table format. And why is that helpful? It just breaks up the visual layout of it, and so it really isolates, and I can say, oh look, my change in y is 25 minus 10. And my change in x is 77 minus 50. So 25 minus 10 is 15. My change in x is 27. If you're not immediately seeing how you can reduce this, you start asking yourself, what can I divide these by? By 2? No. Obviously, they're not even numbers. By 3? Well, yeah. You can divide 15 by 3 and get 5. And 27 by 3 and get 9. So the rate of change is 5/9. What does this mean? That means, okay, so this is change in y, this is change in x. So our y is degrees Celsius, here's y. This is degrees Fahrenheit, that's x. So we're saying, I'll write it in the order, that degrees Celsius increase by 5 for every 9 degrees Fahrenheit. Right? Like this, for every. All right, in this scenario, the x-intercept is, well, this is really, really precise, but let's think about this. When it's 0 degrees Celsius, what is it Fahrenheit? If you pay any attention to that conversion, if you know anything about Celsius, you know that 0 degrees Celsius is when water freezes, and that is also 32 degrees Fahrenheit. So this means that 32 degrees Fahrenheit is 0 degrees Celsius, right? Or we'd say that when it is 32 degrees Fahrenheit, it is 0 degrees Celsius. Okay. Flipping it over. The table shows how the number of peanuts in a jar of peanut butter, and most of you caught this in class, these are backwards. We don't make 1,000 jars out of 2 peanuts. We probably make 2 jars out of 1,000 peanuts. Okay? Now, interesting question, because it says, is this graph of the data a line? So how would we know that? Well, I mean, you certainly could graph it. Right? You could say, okay, this is jars here. But we need to be careful, right? This is 1, 2, 3, 4, 5, 6, 7. We need to make sure that we have an even scale, because our table is not giving us even numbers. And then here we'll say 1,000, 2,000, 3,000, 4,000, 5,000. So there's 1,000, 2,000, 3,000, and oh, don't just go up the points. Remember that it's 5,000. If you do it this way, right, I can fill this in, then I can see that it's there, 1,002, that it's 2,004, that it's 3,005, and that it's 5,007. Now, this is a very imprecise graph, right? I didn't even sit on a grid, but I can certainly tell there is no way to make these fit on a line. Now the numbers will bear that out, right? So look, if this is my x here, and this is my y here, then I'm saying here's a change of 1,000, and here's a change of 2. So the first one would be 1,000 over 2, which would be 500. So that would be my rate of change for the first one. The next one is, again, 1,000, but this time it's only a rate of change of 1. So that would be 1,000 over 1, or 1,000. And here we have one of 2 and of 2,000. So that would be 2,000 over 2, which is 1,000. So you can see that I don't have a constant rate of change, right? The rate of change is different from here to here than it is from these two. And we can sort of see that. This, though not a great graph, you can see these are about in a line. But this, right? So here's a rate of change of 500, and here's a rate of change of 1,000. So they're not all in a line because the rates of change are different. So no, because rates of change are different. And as you identify and interpret the intercepts in the scenario above, you can say, look, I don't know whether this is going to go down or go straight, or there's no way. So, unknown. All right? So that's what we know about lines, is that they have constant rates of change. If the rates of change aren't constant, then it must not be a line. There you go. Good luck, and we'll see you tomorrow.